Right now, a spacecraft launched in 1977 is the fastest human-made object ever to leave our solar system. Voyager 1 screams through interstellar space at 17 kilometers per second. At that speed, you could fly from New York to Los Angeles in under 4 minutes. Yet if you pointed Voyager 1 directly across our galaxy and waited, it would not arrive for over 1,700,000,000 years. You heard that right. Our galaxy is so incomprehensibly vast that even technologies we consider revolutionary would take longer than Earth has been alive to cross it. Tonight, we are going to calculate exactly how long it takes to traverse the Milky Way under every propulsion method humanity has ever conceived or imagined. The numbers will break your intuition permanently. If you enjoy journeys that completely reshape how you see our place in the cosmos, do me a favor and hit that like button and subscribe. It genuinely helps this channel grow and allows me to keep making these explorations for you. Now, with that said, make yourself comfortable. Let's begin. The Milky Way is not what you think it is. When most people picture our galaxy, they imagine a glowing disk of stars spinning elegantly through space, a tidy spiral with neat boundaries and a clearly defined edge. Something you could point to on a map and say, that is where it starts, that is where it ends. The reality is far messier, far larger, and far more terrifying than any classroom diagram has ever shown you. Before we can calculate how long it takes to cross this thing, we need to understand exactly what we are trying to cross. And that question alone turns out to be surprisingly difficult to answer. Let us start with the most basic measurement. The stellar disk of the Milky Way, the flat plane where the vast majority of stars live and orbit, spans approximately 100,000 to 120,000 light-years from edge to edge. Different measurement techniques produce slightly different numbers. Radio telescopes mapping hydrogen gas at the galactic fringes suggest the disk extends a bit farther than optical surveys, tracking visible stars. Infrared observations push the boundary out even further by detecting dim red dwarfs and brown dwarfs that optical telescopes miss entirely. But the scientific consensus hovers around that range. For the purposes of this journey, we will use 100,000 light-years as our working diameter. It is a conservative, well-supported figure that most astronomers accept as a reliable baseline, and it keeps our calculations honest rather than inflated. Now, 100,000 light-years sounds like a number. It rolls off the tongue easily enough. 3 syllables, 2 words, done. But your brain is lying to you when it pretends to understand what that distance actually represents. A single light-year is the distance that light, the fastest thing in the universe, covers in one full year of continuous travel. Light moves at approximately 186,000 miles per second. Not per hour, per second. In the time it took you to listen to that last sentence, light travelled far enough to circle Earth roughly 7.5 times. In one full year of non-stop travel at that velocity, light crosses roughly 5.88 trillion miles. That is 5,880,000,000,000 miles for a single light year. Now multiply that by 100,000. The diameter of our galaxy measures approximately 588 quadrillion miles. In kilometers, the number is even more staggering. 1 light year equals approximately 9.46 trillion kilometers. The full galactic diameter stretches to roughly 946 quadrillion kilometers. Written out in full, that number has 18 digits. If you tried to count from 1 to that number at a rate of 1 per second, you would need over 30 billion years. That is more than twice the current age of the universe. These numbers have no human reference point. They exist purely as mathematical abstractions that describe a physical space so vast that no metaphor can truly capture it. But we will try, because understanding the scale is essential to grasping why crossing this distance is so overwhelmingly, almost absurdly difficult. Here is the first critical distinction most people miss. The Milky Way is not a sphere, it is a disk. a very, very thin disk relative to its width. The average thickness of the stellar disk measures roughly 1,000 to 2,000 light-years, depending on where you measure. Near the galactic center, a dense bulge of older stars swells the thickness to roughly 10,000 light-years above and below the midplane, creating a structure that resembles a fried egg when viewed from the side. But out in the spiral arms where we live, the disk thins dramatically. Compare the 1,500 light-year average thickness to the 100,000 light-year diameter. The galaxy is roughly 50 to 100 times wider than it is tall. If you scaled the Milky Way down to the dimensions of a standard vinyl record, the proportions would actually be remarkably close. We live inside something astonishingly flat. This flatness creates an important distinction when we talk about crossing the galaxy. Crossing it through the thin dimension, punching straight up or down through the disk, covers only 1 to 2,000 light-years. That is still an immense distance by any human standard, but it is a dramatically shorter journey than crossing edge to edge along the diameter. When scientists and science communicators discuss galactic crossing times, they virtually always mean the long way, edge to edge, spanning the full diameter. That is the journey we are interested in. The full 100,000 light-year traverse across the widest dimension of our galactic home. When you hear someone ask how long it would take to cross the Milky Way, this is what they are really asking about, and this is the challenge we are going to take seriously. But the disk is not the only component of the galaxy that matters for defining its true extent. At the center sits a dense, roughly spherical concentration of older, redder stars called the galactic bulge. This structure extends roughly 10,000 light-years above and below the galactic plane, making it significantly thicker than the surrounding disk. The bulge is densely packed with stars, many of them billions of years older than our Sun. It is gravitationally intense, dynamically complex, and it surrounds a supermassive black hole called Sagittarius A star, which contains approximately 4 million times the mass of our Sun, crammed into a region smaller than the orbit of Mercury. Any trajectory that crosses the galaxy through the geometric center would need to contend with this region, and as we will see later, the challenges it presents are not trivial at all. Beyond the bulge, surrounding the entire visible galaxy like an invisible cocoon, stretches an enormous spherical structure called the galactic halo. The halo contains ancient stars, many of them among the oldest objects in the galaxy. It also hosts roughly 150 globular clusters, dense balls of hundreds of thousands to millions of stars that orbit the galactic center on highly elongated paths. But the most significant component of the halo by far is dark matter. This invisible substance, detectable only through its gravitational influence on visible matter, makes up roughly 85% of the galaxy's total mass. The dark matter halo extends vastly beyond the stellar disk. Most estimates place the halo's outer boundary at roughly 200,000 to 300,000 light-years from the galactic center. Some recent studies using stellar streams and the orbits of satellite galaxies like the Large Magellanic Cloud suggest the halo might reach even further, perhaps 400,000 light-years or beyond. The gravitational sphere of influence of the Milky Way, defined by the region where its gravity dominates over the pull of neighboring galaxies, extends further still. This raises a genuine and important question. When we say we want to cross the Milky Way, do we mean the stellar disk, or the full gravitational extent including the dark matter halo? The answer matters enormously. If we use the halo as our boundary, the crossing distance leaps to 400,000 or even 600,000 light-years. That would multiply every single travel time calculation we perform by a factor of 4 to 6. For this script, we will keep our definition focused and practical. The stellar disk, 100,000 light-years, edge to edge. That is where the overwhelming majority of the galaxy's stars, gas, planets, and potential for life resides. It is already an incomprehensibly vast distance. The halo would only make things dramatically worse, and we have more than enough ground to cover with the disk alone. Now here is something most people never think about when they imagine crossing the galaxy. When we talk about making this journey, we instinctively imagine starting from Earth. But Earth does not sit at the edge of the galaxy. Our solar system orbits roughly 26,000 light-years from the galactic center, positioned in a region between the Sagittarius and Perseus spiral arms, in what astronomers call the Orion Spur or Orion Arm. We live in what you might call the galactic suburbs, not in the dense urban core, not in the distant rural outskirts, but somewhere in between. This means we are offset from center, sitting a bit closer to the interior than the outer rim. This position creates an asymmetry in any crossing attempt originating from Earth. If you launched a spacecraft from our solar system and aimed it toward the nearest galactic edge, you would need to travel approximately 24,000 light-years outward through increasingly sparse stellar populations. If you aimed in the other direction, toward the far edge on the opposite side of the galaxy, you would need to cross roughly 74,000 light-years, passing directly through the galactic center and all its hazards along the way. Neither direction offers an easy path, but the difference between 24,000 and 74,000 light-years is enormous. It is the difference between a journey that is merely impossible by current standards and one that is several times more impossible. But a true edge-to-edge crossing, the full 100,000 light-years, requires starting from one rim of the galaxy and travelling all the way to the other. That is the benchmark we will use for every calculation in this episode. Not because starting from Earth is irrelevant, but because the full diameter gives us the most honest, most complete picture of the galaxy's true scale. It forces us to confront the entirety of the Milky Way, rather than just the portion between us and the nearest boundary. Anything less would be underselling what crossing our galaxy truly demands. There is another complication that deserves serious attention. You cannot actually fly in a straight line across the galaxy. The Milky Way is not empty space with stars sprinkled decoratively through it like glitter in a snow globe. It is a dynamic, cluttered, gravitationally complex environment, filled with obstacles that would deflect, delay, damage, or outright destroy any spacecraft attempting a direct crossing. Start with molecular clouds. These are vast regions of dense gas and dust where new stars are actively forming. Some molecular clouds span hundreds of light-years across and contain enough raw material to birth thousands of stellar systems. The Orion Molecular Cloud Complex, one of the nearest large star-forming regions to Earth, stretches roughly 240 light-years in length and contains gas dense enough to block visible light from stars behind it completely. Flying through a molecular cloud at high speed would not be like flying through fog on a highway. The gas densities, while still remarkably low by terrestrial standards, are high enough to create significant drag on a spacecraft traveling at any appreciable fraction of light speed. More critically, these regions contain dense clumps, protostars, and jets of superheated material that represent genuine physical hazards capable of ending any crossing attempt. Then there are the spiral arms themselves. The Milky Way has at least 4 major spiral arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm, along with several smaller spurs and branches, including our own Orion arm. These arms are not solid walls of stars. They are density waves, regions where stars, gas, and dust concentrate more tightly as material orbits through them. Passing through a spiral arm means encountering higher stellar densities, more frequent radiation sources including hot young O and B-type stars that flood their surroundings with ultraviolet radiation, and greater gravitational complexity from clustered mass. The spaces between spiral arms are comparatively sparse, offering cleaner transit corridors but not empty ones. Any realistic crossing trajectory would need to account for the spiral structure and carefully plan routes that minimize exposure to the densest, most hazardous regions. The galactic center presents by far the most formidable obstacle on any crossing path. Within the inner few thousand light-years of the galaxy, stellar densities skyrocket. Stars are packed so closely together that mutual gravitational interactions become frequent and violent. Many stars orbit the central supermassive black hole at velocities exceeding several thousand kilometers per second, creating a chaotic dynamical environment where trajectories become unpredictable. The radiation environment near the core is intense. X-ray binaries, magnetars, energetic particle jets, and magnetic fields, far stronger than anything in the outer disk, bombard the inner galaxy with radiation that would be lethal to both biological life and sensitive electronic equipment. A spacecraft crossing the full diameter of the galaxy in a geometrically straight line would need to pass directly through or uncomfortably near this region. The gravitational influence of Sagittarius A star, while not dangerous at distances of several hundred light-years, creates a complex warping of space-time that would require precise navigation to traverse without catastrophic trajectory deflection. Even in the quieter regions of the galactic disk, far from the core and between the spiral arms, hazards persist. Rogue planets, estimated to number in the billions, drift through interstellar space unbound to any star and invisible to almost every detection method until you are dangerously close. Stellar remnants like neutron stars and stellar mass black holes lurk in the darkness, some spinning rapidly and emitting beams of radiation, others sitting silently with gravitational fields strong enough to capture or deflect passing objects. High-energy cosmic rays permeate the entire interstellar medium, creating a constant low-level radiation bath. And the interstellar medium itself, the thin but ever-present soup of hydrogen atoms, dust grains and charged particles filling the space between stars, becomes a severe problem at high velocities. At a significant fraction of light speed, individual hydrogen atoms impact a spacecraft's hull with the energy of high-speed bullets. We will explore that particular nightmare in detail when we discuss relativistic travel. For now, the essential point is this. Crossing the galaxy is not a simple point-to-point transit through peaceful emptiness. It is a navigation challenge of extraordinary complexity through a dynamic, evolving, hazard-filled environment spanning a distance that dwarfs anything humanity has ever attempted. So how do astronomers actually measure these vast galactic distances? How do we know with confidence that the galaxy is 100,000 light-years across and not 50,000 or 200,000? The answer involves multiple independent and overlapping techniques, each contributing its own strengths and limitations to the picture. The most fundamental technique is stellar parallax. As Earth orbits the Sun over the course of a year, nearby stars appear to shift very slightly against the background of more distant stars. This tiny apparent wobble, measured in fractions of an arc-second, allows astronomers to calculate the distance to a star using basic trigonometry. The European Space Agency's Gaia spacecraft, launched in 2013, has measured parallax distances for nearly 2 billion stars with extraordinary precision, creating the most detailed three-dimensional map of the Milky Way ever produced. But parallax has a range limit. Beyond roughly 30,000 light-years, the angular shifts become too minuscule to measure reliably, even with Gaia's incredible instruments. The galaxy is simply too large for parallax alone to span. For more distant objects, astronomers turn to spectroscopic methods. By analyzing the light spectrum of a star, scientists can determine its intrinsic properties, its temperature, surface gravity, and chemical composition. These properties reveal what type of star it is, and therefore how intrinsically luminous it should be. Comparing this known intrinsic brightness to how dim the star appears from Earth reveals its distance. This technique works across the entire galaxy but requires careful calibration and is vulnerable to errors introduced by interstellar dust, which dims and reddens starlight as it passes through, potentially making stars appear farther away than they actually are. Radio astronomy provides another indispensable tool for galactic mapping. Hydrogen gas, the most abundant element in the universe, emits radiation at a characteristic wavelength of 21 centimeters. Radio telescopes can detect this emission from hydrogen clouds throughout the entire galactic disk, even through the thick dust that completely blocks visible light from reaching us. By measuring the Doppler shift of this hydrogen emission, astronomers can determine how fast the gas is moving toward or away from Earth. Combined with mathematical models of galactic rotation, These velocity measurements reveal the distance to gas clouds across the full extent of the disk. This technique was instrumental in first mapping the spiral arm structure of the Milky Way back in the 1950s and remains critical for establishing the galaxy's overall dimensions. Masers, naturally occurring sources of amplified microwave radiation found in active star-forming regions, provide among the most precise distance measurements available anywhere in astronomy. Using a technique called very long baseline interferometry, which links radio telescopes separated by thousands of kilometers into a single virtual instrument with extraordinary angular resolution, astronomers can measure parallax distances to masers across the entire galaxy. The BSCL survey, standing for Bar and Spiral Structure Legacy Survey, used this maser parallax technique to pin down the distance from our solar system to the galactic center at approximately 26,000 light-years, with a precision of just a few percent. These measurements also dramatically refined our understanding of the galaxy's rotation speed, its spiral arm geometry, and its overall scale. Cepheid variable stars provide yet another crucial rung on the distance ladder. These pulsating stars brighten and dim, with periods that correlate precisely and predictably with their intrinsic luminosity. Measure the pulsation period of a Cepheid, and you know its true brightness. Compare that true brightness to how bright it appears from Earth, accounting for dust dimming, and you can calculate its distance with high confidence. Cepheids were historically essential in establishing the scale of our galaxy in the early 20th century, and they remain important calibration standards for modern galactic cartography. Each of these techniques, parallax, spectroscopy, radio hydrogen mapping, maser interferometry, and Cepheid variables, contributes independently to a remarkably consistent picture. The stellar disk of the Milky Way measures approximately 100,000 to 120,000 light-years in diameter. Our solar system sits roughly 26,000 light-years from the center, slightly inside the corrotation radius where the orbital speed of stars matches the rotation speed of the spiral density wave pattern. The disk averages roughly 1,500 to 2,000 light-years in thickness in the outer regions, with a central bulge reaching up to 20,000 light-years across. These numbers are not estimates based on a single observation or a single method. They are the convergent product of decades of independent measurements from ground-based observatories, space telescopes, and radio arrays working across virtually every wavelength of the electromagnetic spectrum. But knowing the dimensions intellectually is only half the battle. Feeling the scale, understanding it emotionally in a way that goes beyond abstract quadrillions, requires a different kind of approach. So let us try one analogy. Just one, because no single comparison can truly capture these distances, but one carefully chosen analogy is better than staring at numbers that have lost all meaning. Imagine shrinking the entire Milky Way galaxy down until it fits neatly across the continental United States, coast to coast, roughly 4,000 kilometers from New York to Los Angeles. At this scale, each real light-year of galactic distance corresponds to roughly 40 meters on the ground, about the length of an Olympic swimming pool. Stars that are 10 light-years apart in reality would be separated by 400 meters at this scale, roughly 4 city blocks. That sounds manageable. But here is where the analogy strikes. Our entire solar system, from the Sun all the way out to the orbit of Neptune, a region spanning roughly 9 billion kilometers of real space, would shrink down to a size smaller than a single atom. Not smaller than a grain of sand, not smaller than a human cell, smaller than an individual atom. You would need an electron microscope just to find it. The distance from our Sun to the nearest neighbouring star, Proxima Centauri, approximately 4.24 light-years away, would measure roughly 170 meters at this scale. Less than 2 football fields, set within a country-sized galaxy where your entire planetary system is invisible to the naked eye. That is the scale we are dealing with. A cosmos in which everything you have ever known, every place you have ever been, every planet humanity has ever photographed, shrinks to atomic invisibility when viewed against the full canvas of our galaxy. And we are about to try crossing that canvas using rockets. There is one final thing we need to establish before we start putting spacecraft on the clock. The Milky Way is not a frozen, static object hanging in space like a painting on a wall. It is rotating. It is moving through space at enormous velocity relative to the cosmic microwave background. Its stars are orbiting the galactic center independently, each on its own trajectory, each at its own speed. The structure itself is alive with motion, and that motion has profound consequences for anyone trying to cross it. For now, we are setting the stage. And the stage is defined by one number that contains everything we need to understand about the challenge ahead. 100,000 light-years, 588 quadrillion miles, 946 quadrillion kilometers. A disk so thin relative to its width that it resembles a cosmic vinyl record, yet so impossibly vast that light, the fastest phenomenon permitted by the laws of physics, needs 100,000 years to span it. A photon that left the far edge of the galaxy around the time the last ice age was releasing its grip on Earth is still in transit right now, still racing through interstellar space at 186,000 miles per second, still not here, and it will not arrive for tens of thousands of years yet. That is the distance we are about to ask a spacecraft to cross. Not light, which is already the ultimate speedster of the cosmos, a spacecraft. A machine built by a species that has existed for roughly 300,000 years on a small rocky planet orbiting an average star in the galactic suburbs. A machine made of metal and fuel and extraordinary ambition. The numbers are about to get deeply uncomfortable, and they are only going to get worse from here. Part 2. The Crawl. Travel time at current and near-future spacecraft speeds. On September 5th, 1977, a spacecraft weighing roughly 825 kilograms launched from Cape Canaveral atop a Titan IIIe rocket. Its primary mission was to study Jupiter and Saturn. Nobody expected it to become humanity's most distant ambassador. But nearly 5 decades later, Voyager 1 has crossed into interstellar space and continues transmitting faint signals back to Earth from a distance of over 24 billion kilometers. It is the farthest any human-made object has ever traveled, and it is moving fast. Voyager 1 races through the void at approximately 17 kilometers per second relative to the Sun. That translates to roughly 61,000 kilometers per hour, or about 38,000 miles per hour. At that velocity, you could travel from London to Sydney in 25 minutes. You could circle the entire Earth in just over an hour. By every terrestrial standard, Voyager 1 is extraordinarily fast. Now let us point it at the far edge of the Milky Way and start counting. The galaxy stretches 100,000 light-years across. 1 light-year equals approximately 9.46 trillion kilometers. So our crossing distance measures roughly 946 quadrillion kilometers. Voyager 1, at 17 kilometers every single second, would need approximately 1,760,000,000 years to complete that crossing. Let that number settle for a moment. 1,760,000,000 years. That is not merely longer than human civilization. It is longer than the entire Phanerozoic eon, the geological period encompassing all of complex multicellular life on Earth. When Voyager 1 reached the halfway point of its galactic crossing, more time would have elapsed than the entire history of animals, plants, fungi, and every complex organism that has ever lived on this planet. Trilobites, dinosaurs, mammals, humans, all of it would fit inside less than 1/3 of the journey. Voyager 1 would still have over 1 billion years of travel remaining, and this is the fastest interstellar spacecraft humanity has ever launched. Let us compare with another record holder. NASA's New Horizons probe, launched in January 2006, left Earth faster than any spacecraft before it. Its initial departure velocity reached approximately 16.26 kilometers per second relative to Earth, fast enough to pass the Moon's orbit in just 9 hours. After a gravity assist from Jupiter that boosted its speed, New Horizons raced onward to its historic flyby of Pluto in July 2015. But here is a detail that matters enormously for our calculation. New Horizons has been gradually slowing down ever since that Jupiter encounter. Without continuous thrust, spacecraft in interstellar space lose velocity over time due to the faint but persistent gravitational pull of the Sun and the surrounding stellar environment. By the time New Horizons reaches interstellar space, its velocity will have decreased to roughly 13 to 14 kilometers per second. Even using its peak speed of 16.26 kilometers per second, and generously assuming it could maintain that pace indefinitely, the galactic crossing time works out to approximately 1,840,000,000 years, marginally worse than Voyager 1. Two spacecraft separated by nearly 3 decades of technological advancement, and the difference in galactic crossing time amounts to a rounding error within the same geological eon. This should tell you something profound about the futility of current propulsion technology at galactic scales. The best we have built so far, the absolute pinnacle of human spaceflight engineering, produces crossing times measured in billions of years. The galaxy does not care about our engineering milestones. At these distances, the difference between our fastest and second fastest spacecraft is cosmically meaningless. But perhaps we are being unfair. Voyager 1 and New Horizons were never designed for speed. They were designed for scientific observation, built to study planets, not to race across the cosmos. What about a spacecraft optimized purely for velocity? What about the fastest object humans have ever created? Enter the Parker Solar Probe. Launched in August 2018, this NASA mission was designed to fly closer to the Sun than any previous spacecraft, diving repeatedly through the Sun's outer atmosphere to study solar wind and magnetic fields. To reach these close solar approaches, the Parker Solar Probe uses a series of gravity assists from Venus combined with the Sun's own gravitational pull to accelerate to extraordinary velocities. During its closest perihelion passages, the probe reaches speeds of approximately 192 kilometers per second. That is roughly 692,000 kilometers per hour, or about 430,000 miles per hour. At that velocity, you could travel from Earth to the Moon in roughly 33 minutes. Parker Solar Probe is, by a wide margin, the fastest object humanity has ever built. It moves more than 11 times faster than Voyager 1. Surely this makes a difference at the galactic scale. Let us run the numbers. 946 quadrillion kilometers divided by 192 kilometers per second gives approximately 156 million years. 156 million years. A massive improvement over Voyager 1's billion-plus timeline. And yet, think about what 156 million years actually means. 156 million years ago, dinosaurs dominated every continent on Earth. Tyrannosaurus rex had not yet evolved. Flowering plants were just beginning to diversify. The Atlantic Ocean was significantly narrower. India was still an island drifting northward through the ancient Tethys Sea. The entire arc of evolution from mid-Cretaceous dinosaurs to modern human civilization, including the asteroid impact that ended the Mesozoic era, the rise of mammals, the evolution of primates, the development of language, agriculture, and spaceflight, all of that fits comfortably within the time it would take the Parker Solar Probe to cross our galaxy. The fastest thing we have ever constructed would need more time than the age of dinosaurs just to get from one edge to the other. And there is a critical asterisk on this calculation. The Parker Solar Probe only reaches 192 kilometers per second during its closest approach to the Sun. This velocity is achieved through gravitational acceleration, not propulsion. The probe speeds up as it falls toward the Sun and slows down as it climbs back out on the other side of its orbit. It cannot sustain this speed on a straight-line trajectory across interstellar space. In practice, a spacecraft using the Parker Solar Probe's actual engine technology for an interstellar crossing would travel far slower than 192 kilometers per second. The real crossing time would be significantly longer than 156 million years. But even accepting the optimistic number, it remains geological in scale. a duration that would see entire ecosystems rise and collapse thousands of times over before the journey ended. Let us step back from specific missions and examine propulsion categories more broadly. What do chemical rockets, the workhorses of the entire space age, actually offer for galactic travel? Chemical rockets generate thrust by burning fuel and expelling the resulting hot gas at high speed through a nozzle. Every rocket that has ever carried a human into space, every Saturn V that launched Apollo missions to the moon, every space shuttle that serviced the International Space Station, every Falcon 9 that delivers satellites to orbit, all of them use chemical propulsion. The fundamental physics of chemical rocketry are governed by the energy density of chemical bonds. When hydrogen burns with oxygen, or when kerosene combusts in a rocket engine, the maximum energy available per kilogram of fuel is fixed by chemistry. This sets an upper limit on how fast exhaust gases can exit the nozzle, a quantity called specific impulse, which directly determines how much velocity change a rocket can achieve for a given amount of fuel. The best chemical rocket engines achieve a specific impulse of roughly 450 seconds. This translates to exhaust velocities of approximately 4.4 kilometers per second. For a spacecraft to reach high speeds using chemical propulsion, it must carry enormous quantities of fuel. The tyranny of the rocket equation, formulated by Konstantin Tsiolkovsky in 1897, dictates that each additional increment of speed requires exponentially more fuel. To accelerate a modest payload to even 30 kilometers per second using chemical rockets would require fuel masses hundreds of times greater than the payload itself. Achieving velocities beyond 50 kilometers per second becomes practically impossible without staging and gravity assists, because the fuel required would outweigh any conceivable spacecraft by absurd margins. In practice, chemical rockets on deep space trajectories achieve sustained velocities in the range of 11 to 15 kilometers per second. The Space Shuttle's orbital velocity was approximately 7.8 kilometers per second, but that was in low Earth orbit, not on an interstellar trajectory. For a spacecraft leaving the solar system on chemical propulsion alone, realistic speeds fall in the range of 12 to 17 kilometers per second. At 15 kilometers per second, the galactic crossing time calculates to approximately 2 billion years. At the theoretical maximum of what chemical propulsion might achieve with every conceivable optimization, perhaps 40 to 50 kilometers per second, using extreme multi-stage designs and planetary gravity assists, the crossing time drops to roughly 600 million years, still longer than the entire history of complex animal life on Earth. Chemical rockets are not going to cross the galaxy. The energy locked in chemical bonds is simply insufficient. We need something fundamentally more powerful. The most obvious step up from chemical propulsion is nuclear thermal propulsion. The concept is straightforward. Instead of burning chemical fuel, use a nuclear fission reactor to heat a propellant, typically hydrogen gas, to extremely high temperatures before expelling it through a nozzle. Because nuclear reactions release roughly 1,000,000 times more energy per kilogram than chemical reactions, nuclear thermal rockets can achieve significantly higher exhaust velocities and therefore higher specific impulse. This is not speculative technology. NASA and the Atomic Energy Commission built and tested nuclear thermal rocket engines during the 1960s under a program called NERVA, which stood for Nuclear Engine for Rocket Vehicle Application. The NERVA engines successfully demonstrated specific impulses of roughly 850 seconds, nearly double that of the best chemical engines. They worked, they were reliable. The program was cancelled in 1973 due to budget cuts and shifting political priorities, not because the technology failed. Modern proposals for nuclear thermal propulsion have revived the NERVA concept with updated materials and reactor designs. NASA's current efforts, including the Draco program in partnership with DARPA, aim to demonstrate a nuclear thermal engine in orbit within the next several years. These modern designs target specific impulses of 900 seconds or higher. With sustained nuclear thermal thrust, a spacecraft could theoretically achieve velocities of roughly 30 to 50 kilometers per second for an interstellar trajectory. That is approximately double to triple what chemical rockets can manage. At 50 kilometers per second, crossing 100,000 light-years takes approximately 600 million years. At 30 kilometers per second, the crossing stretches to roughly 1 billion years. Nuclear thermal propulsion is genuinely superior to chemical rockets. It represents a real technological leap, but against the scale of the galaxy, it barely moves the needle. We have gone from billions of years to hundreds of millions of years, an improvement measured in geological eons, yet still utterly incompatible with any meaningful definition of travel. But nuclear thermal propulsion is not the only way to harness nuclear energy. There is a step beyond heating propellant with a fission reactor. You can try to replicate the process that powers the sun itself. Nuclear fusion, the merging of light atomic nuclei into heavier ones, releases roughly 4 times more energy per kilogram than nuclear fission. If you could build a rocket engine that ran on controlled fusion reactions, you would leap beyond the performance ceiling of nuclear thermal designs by a substantial margin. This is not purely speculative. In 1973, the British Interplanetary Society launched a formal engineering study called Project Daedalus to design an unmanned interstellar probe capable of reaching Barnard's star, roughly 6 light-years away, within a human lifetime. The design used inertial confinement fusion, a technique where tiny pellets of deuterium and helium-3 fuel are compressed and ignited by powerful electron beams, roughly 250 times per second. Each micro-explosion would release energy against a magnetic nozzle, generating thrust far beyond what any fission system could achieve. The Daedalus team calculated that their 2-stage vehicle, which would weigh approximately 54,000 tons fully fueled, could accelerate to roughly 12% of light speed. 12%. That is 36,000 kilometers per second, roughly 2,000 times faster than Voyager 1. A successor study called Project Icarus, launched in 2009, revisited the Daedalus concept with updated physics and engineering. Icarus explored variations including deceleration capability, which Daedalus lacked, and alternative fusion fuel cycles. Both studies concluded that fusion propulsion could realistically achieve velocities in the range of 10 to 15% of light speed, provided the engineering challenges of sustained ignition, fuel containment, and magnetic nozzle design could be solved. At 12% of light speed, crossing 100,000 light-years takes approximately 833,000 years. A significant improvement over nuclear thermal propulsion's billion-year timescales, and roughly comparable to the nuclear pulse propulsion numbers we will examine next. But 833,000 years remains staggeringly long. Modern humans did not exist 833,000 years ago. Homo heidelbergensis roamed Europe and Africa. The Acheulean hand axe was the height of technology. 833,000 years from now, whatever species descends from us will likely bear as little resemblance to modern humans as we bear to those distant ancestors. Fusion propulsion represents a genuine technological frontier. Unlike nuclear pulse propulsion, which requires detonating nuclear weapons, fusion engines could theoretically operate cleanly and continuously. Several nations and private ventures are currently pursuing fusion power for terrestrial energy production, and while no one has yet achieved sustained net energy fusion on Earth, the physics is well understood. The engineering is the barrier, not the science. But even if fusion propulsion is perfected exactly as the Daedalus and Icarus studies envisioned, it delivers crossing times measured in hundreds of thousands of years. A transformative technology for reaching nearby stars within a few decades. An exercise in futility for crossing the galaxy within any recognizable civilizational timeframe. What about something more radical? What about nuclear pulse propulsion? In the late 1950s, a team of physicists and engineers at General Atomics conceived one of the most audacious propulsion concepts in history. Project Orion proposed using nuclear explosions, actual nuclear bombs, detonated behind a massive pusher plate to propel a spacecraft to extraordinary velocities. The concept sounds insane, and in many ways it was, but the physics was entirely sound. Freeman Dyson, Ted Taylor, and their colleagues calculated that a large Orion vehicle could achieve specific impulses of tens of thousands of seconds, orders of magnitude beyond anything chemical or nuclear thermal engines could reach. An Orion spacecraft the size of a small city could theoretically accelerate to 3 to 5% of the speed of light. 3% of light speed equals approximately 9,000 kilometers per second. 5% equals roughly 15,000 kilometers per second. These velocities are transformative compared to everything we have discussed so far. Let us calculate. At 3% of light speed, crossing 100,000 light-years takes approximately 3,300,000 years. At 5% of light speed, the crossing shrinks to roughly 2 million years. For the first time in our calculations, we have dropped below the geological timescale and entered the anthropological timescale. 2 to 3 million years ago, our ancestors in the genus Homo were just beginning to emerge in Africa. Homo habilis was crafting the first crude stone tools. The journey has compressed from billions of years to millions. That represents an improvement by a factor of roughly 1,000 compared to Voyager 1. It is extraordinary progress. And yet 3 million years is still incomprehensible as a travel time. No human institution has lasted more than a few thousand years. No biological species remains unchanged for millions of years. The beings who launched an Orion spacecraft would bear no relationship, culturally, genetically, or perhaps even cognitively, to the beings who arrived at the destination. 3 million years is enough time for entire civilizations to rise, flourish, collapse, and be forgotten thousands of times over. The beings who departed would share nothing with the beings who arrived. Project Orion was never built. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear detonations in space, effectively killing the project. Political and environmental concerns outweighed the extraordinary performance the concept offered, but the physics remains valid. Nuclear pulse propulsion represents one of the few technologies humanity has seriously studied that could approach low single-digit percentages of light speed. And even at those speeds, the galaxy exacts millions of years of patience. There is one more propulsion concept that deserves examination before we leave the realm of reaction-based engines. Antimatter propulsion represents the absolute theoretical ceiling of what chemical, nuclear, or any other fuel-based system can achieve. When matter meets antimatter, both are annihilated completely, converting 100% of their combined rest mass into energy, according to Einstein's famous equation relating energy to mass and the speed of light squared. No other reaction in physics comes close to this efficiency. Chemical combustion converts roughly 1/10,000,000th of fuel mass into energy. Nuclear fission converts about 0.1%. Nuclear fusion achieves roughly 0.7%. Antimatter annihilation converts 100%. It is the perfect fuel. In principle, an antimatter rocket would combine matter and antimatter in a controlled reaction chamber, directing the resulting high-energy particles, primarily pions and gamma rays, out of a magnetic nozzle to generate thrust. The exhaust velocity would approach the speed of light itself, giving the engine a specific impulse millions of times greater than chemical rockets. Theoretical studies suggest that an optimized antimatter drive could accelerate a spacecraft to perhaps 40 to 70% of the speed of light, depending on design assumptions about how efficiently the annihilation products can be directed into useful thrust. At 40% of light speed, crossing 100,000 light-years takes 250,000 years. At 70%, it shrinks to approximately 143,000 years. These numbers represent another massive leap forward compared to fusion, or nuclear pulse propulsion. We have moved from hundreds of thousands of years into a range where the crossing time is comparable to the age of anatomically modern Homo sapiens as a species. Still immense, but compressing. The problem with antimatter propulsion is not physics. The physics is flawless. The problem is production. Antimatter does not exist naturally in significant quantities anywhere in the known universe. Every antiproton and positron must be manufactured in particle accelerators through energy-intensive collisions. The global output of all particle physics facilities on Earth amounts to approximately 10 to 15 nanograms of antimatter per year. 1 nanogram is 1 billionth of a gram. To fuel even a modest interstellar spacecraft for a galactic crossing would require hundreds or thousands of tons of antimatter. At current production rates, manufacturing a single gram would take roughly 100 million years, approximately 7 times the current age of the universe. The cost is equally prohibitive. Current estimates place antimatter production at roughly $62.5 trillion per gram, making it by far the most expensive substance that has ever existed. These figures reflect the fundamental inefficiency of current production methods, and future technologies might reduce costs by orders of magnitude. But the gap between nanograms per year and thousands of tons is so vast that no foreseeable improvement in production technology closes it within any meaningful time frame. Antimatter propulsion is theoretically supreme and practically non-existent. It represents the hard ceiling of what reaction-based engines can achieve, and even at that ceiling, the galaxy still demands over 100,000 years of travel. The perfect fuel is still not good enough for the imperfect reality of galactic scale. Perhaps we should consider the opposite approach. Instead of brute force explosions, what about quiet, patient, relentless acceleration? Ion propulsion and solar sails represent technologies that sacrifice thrust for efficiency, producing tiny forces sustained over very long periods to build up impressive velocities. NASA's Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres, used an ion propulsion system that expelled xenon ions at velocities of roughly 30 kilometers per second, far higher than the exhaust velocities of chemical rockets. But the thrust was minuscule, approximately 90 millinewtons. That is roughly the force you would feel if someone placed 3 sheets of paper on your palm. Dawn took nearly 4 years of continuous thrusting to change its velocity by just 10 kilometers per second. The engine was extraordinarily efficient in terms of fuel consumption, but painfully slow in terms of actual acceleration. Scaling ion propulsion up for interstellar travel faces fundamental challenges. The electricity needed to power the ion engines must come from somewhere. Solar panels become useless beyond the outer solar system, where sunlight fades to negligible levels. Nuclear power sources like radioisotope, thermoelectric generators produce limited electricity. Even optimistic projections for nuclear electric ion drives suggest achievable cruise velocities of perhaps 50 to 100 kilometers per second for an interstellar probe. At 100 kilometers per second, the galactic crossing takes approximately 300 million years. Better than chemical rockets, comparable to nuclear thermal, but still firmly in the hundreds of millions of years category. Solar sails offer an intriguing alternative. Instead of carrying fuel, a solar sail spacecraft uses the pressure of sunlight itself, photons from the sun bouncing off a large reflective surface, to generate thrust. The advantage is that no fuel is needed. The disadvantage is that solar radiation pressure is exceptionally weak, and it decreases with the square of the distance from the sun. A solar sail works well in the inner solar system, but becomes nearly useless in the outer solar system where sunlight is thousands of times dimmer. The Planetary Society's LightSail 2 mission demonstrated the concept in Earth orbit, and Japan's Icaros probe successfully used a solar sail during a Venus flyby. But achieving interstellar velocities with sunlight alone requires either enormous sails or very close solar approaches to maximize photon pressure. The most optimistic solar sail concepts for interstellar probes suggest velocities of perhaps 100 to 300 kilometers per second if the sail performs an extremely close pass by the sun, diving to within a few solar radii before unfurling and riding the intense radiation outward. At 300 kilometers per second, the galactic crossing time comes to approximately 100 million years, roughly the time since the late Cretaceous period. There is one hybrid concept that deserves mention. The Breakthrough Starshot initiative, announced in 2016, proposes using powerful ground-based lasers to accelerate tiny, gram-scale spacecraft equipped with light sails to approximately 20% of light speed. This would be sufficient to reach the nearest star system, Alpha Centauri, in roughly 20 years. The concept is designed for nearby interstellar targets, not galactic crossing, and it faces enormous engineering challenges, including aiming a laser beam precisely enough to hit a sail centimeters across at distances of millions of kilometers. But even if we imagined scaling Breakthrough Starshot up to push a larger spacecraft to 20% of light speed, which is far beyond anything the project currently envisions, the galactic crossing would still take 500,000 years. 500,000 years. Modern Homo sapiens have existed for roughly 300,000 years. The entire history of our species would fit inside the crossing with room to spare. Let us now step back and look at the full picture of what we have calculated. The pattern is devastating in its clarity. At Voyager 1 speeds of 17 kilometers per second, crossing the galaxy takes approximately 1,760,000,000 years. At New Horizons speeds, roughly 1,840,000,000 years. At Parker Solar Probe peak velocity, approximately 156 million years. At the best chemical rockets can theoretically manage, roughly 600 million to 2 billion years depending on the scenario. At nuclear thermal propulsion speeds, approximately 600 million to 1 billion years. At nuclear pulse propulsion speeds using Project Orion concepts, roughly 2 to 3 million years. At optimistic ion drive velocities, approximately 300 million years. At solar sail velocities with close solar passes, roughly 100 million years. At a hypothetically scaled-up breakthrough starshot velocity of 20% light speed, 500,000 years. Every single number on that list exceeds the entire span of recorded human civilization by factors of hundreds to millions. The shortest crossing time we have calculated using any propulsion technology humanity has ever built, tested, or seriously designed is still measured in millions of years. The longest exceeds the age of complex life on Earth. The galaxy is simply too large and our machines are simply too slow for current or near-future technology to bridge the gap in any time frame meaningful to human experience. There is a pattern buried in these numbers that reveals something fundamental about the problem. Each major leap in propulsion technology, from chemical to nuclear thermal to nuclear pulse, improves crossing times by roughly a factor of 3 to 10. Chemical to nuclear thermal cuts the time by approximately half. Nuclear thermal to nuclear pulse cuts it by a factor of roughly 300 to 500. These are significant improvements in engineering terms, but the galaxy demands improvements by factors of millions before crossing times shrink to anything a civilization could endure. Incremental progress in propulsion technology cannot solve this problem. The gap between what we can build and what the galaxy requires is not an engineering gap. It is a chasm measured in orders of magnitude so vast that evolutionary biology changes species faster than our rockets can deliver them. This is the wall that galactic scale travel slams into when you use realistic propulsion. Not a wall of physics exactly, because physics does permit faster travel. Not a wall of engineering, because better engines can certainly be built. It is a wall of scale. The galaxy is so large that even technologies we consider revolutionary, technologies that would transform interplanetary travel within our solar system, become laughable when measured against 100,000 light-years. A nuclear thermal engine that could send astronauts to Mars in 3 months cannot cross the galaxy in less than 600 million years. The technology that makes us masters of the solar system makes us prisoners of the galaxy. And yet, we have not yet explored the one variable that changes everything. Speed. Real speed. Not the tens of kilometers per second our current engines produce. Not even the thousands of kilometers per second that nuclear pulse propulsion might achieve. We are talking about velocities where the very fabric of space-time begins to distort, where clocks slow down, where distances contract, where the rules of classical physics surrender to something far stranger. What happens when we stop crawling and starts sprinting at a meaningful fraction of the speed of light. The numbers transform, but so do the laws of physics governing the journey. And those laws introduce consequences that are as beautiful as they are disturbing. The galaxy is about to become a very different kind of challenge. Everything we have calculated so far operated within the comfortable realm of classical physics, Newtonian mechanics, straightforward arithmetic, distance divided by speed equals time. The math was simple. The results were horrifying. Billions of years for our fastest existing spacecraft. Millions of years even for the most ambitious nuclear propulsion concepts ever designed. But every one of those calculations assumed that the universe behaves the same way at all speeds. It does not. When you start moving at a significant fraction of the speed of light, the universe changes its rules. Time itself bends, distances contract. The relationship between what a traveler experiences and what an outside observer measures diverges in ways that feel like science fiction, but a confirmed experimental fact. This is the realm of special relativity, and it is the only place where galactic crossing times begin to shrink toward anything remotely approachable. The question is whether they shrink enough. Let us begin at the bottom of the relativistic ladder. 1% of the speed of light. That translates to approximately 3,000 kilometers per second, or roughly 10.8 million kilometers per hour. This velocity is staggeringly fast by any engineering standard. It is roughly 16 times faster than the Parker Solar Probe at its peak, and roughly 176 times faster than Voyager 1. No existing or currently planned propulsion technology can reach this speed, though some advanced concepts like nuclear pulse propulsion and laser-driven sails approach the low single-digit percentages of light speed in theoretical projections. At 1% of light speed, crossing 100,000 light-years takes 10 million years. The math is direct. If you travel at 100th the speed of light, you need 100 times longer than light to cover the same distance. 100,000 years multiplied by 100 equals 10 million years. At this velocity, relativistic effects are negligible. Time dilation at 1% of light speed amounts to a correction of roughly 1 part in 20,000. The traveller's clock would differ from the observer's clock by only a few hundred years over the entire 10 million year journey. Functionally irrelevant, 10 million years is a dramatic improvement over the billions of years that chemical rockets demand. We have leaped from geological timescales into what you might call deep evolutionary timescales, but it remains utterly incomprehensible as a travel duration. 10 million years ago, our ancestors were small-bodied apes in Africa. The Mediterranean Sea had recently reflooded after drying up almost completely during the Messinian salinity crisis. Mammoths did not yet exist. Grasslands were still spreading across continents that looked substantially different from their modern configurations. An entire epoch of primate evolution, the emergence of bipedalism, the development of tool use, the branching of the hominin family tree into dozens of species, and the eventual rise of Homo sapiens, all of that fits within 10 million years. A spacecraft launched at 1% of light speed, when our ancestors first diverged from the lineage leading to modern chimpanzees, would just now be arriving at the far edge of the galaxy. Let us go faster. 10% of light speed, approximately 30,000 kilometers per second, 108 million kilometers per hour. This is the speed that serious interstellar mission concepts tend to target as an aspirational goal for far future technology. At 10% of light speed, the crossing time drops to 1 million years. A further tenfold improvement. Relativistic effects at this velocity begin to emerge but remain modest. The Lorentz factor, the mathematical quantity that governs time dilation and length contraction in special relativity, equals approximately 1.005 at 10% of light speed. This means the traveller's experience time would be roughly 99.5% of the observer's time. Over a million-year journey, the traveller would experience approximately 5,000 fewer years than an observer watching from a stationary reference frame. Noticeable if you are doing precision physics. but practically meaningless against a million-year baseline. 1 million years is the timescale on which Homo sapiens as a species has existed. Modern humans appeared in Africa roughly 300,000 years ago. Our broader genus Homo extends back approximately 2 to 3 million years. A civilization that launched a ship at 10% of light speed around the time the first anatomically modern humans walked the Earth would still have 700,000 years of travel remaining. The species that launched the ship would likely not exist by the time it arrived. Evolution does not wait. Genetic drift, natural selection, and random mutation would transform any population isolated on a spacecraft for 1 million years into something biologically unrecognizable compared to the founders. Now let us push into the range where relativity stops being a footnote and becomes a central character in the story. 50% of the speed of light, 150,000 kilometers per second, 540 million kilometers per hour, half the cosmic speed limit. For a stationary observer watching this spacecraft cross the galaxy, the journey takes 200,000 years. That calculation is still simple division. 100,000 light years divided by half the speed of light equals 200,000 years. But now, something strange begins happening on board the ship. At 50% of light speed, the Lorentz factor rises to approximately 1.155. This means that time on the ship runs slower than time for the stationary observer by a factor of roughly 15%. The travelers do not experience 200,000 years. They experience approximately 173,000 years. The difference, roughly 27,000 years, may seem small against the total journey, but it represents a real, physical, measurable discrepancy. If the travelers carried a clock synchronized with an identical clock left behind at the departure point, the two clocks would disagree by 27,000 years when the journey ended. This is not an illusion or a mathematical trick. Time genuinely passes more slowly for objects moving at high velocities. This phenomenon has been confirmed experimentally using atomic clocks on aircraft, GPS satellites that must correct for relativistic time offsets, and particle accelerators where unstable particles survive far longer than their rest frame lifetimes predict because they are moving at substantial fractions of light speed. At 50% of light speed, the time savings from relativity amount to roughly 13% of the journey duration, meaningful in physics, but not transformative for our problem. 173,000 years is still longer than the entire history of human civilization by a factor of roughly 30. The travelers would need to sustain a functioning spacecraft, a viable population, and a coherent mission purpose for longer than Homo sapiens has existed as a species. Relativity helps, but at 50% of light speed, it does not help enough. 90% of light speed, 270,000 kilometers per second. Now relativity asserts itself forcefully. The Lorentz factor at 90% of light speed equals approximately 2.29. For the stationary observer, the crossing still takes approximately 111,000 years. Since the ship covers 100,000 light years at 90% of light speed, but the travelers experience something profoundly different. Their clocks, their biological aging, their entire subjective experience of time runs slower by that Lorentz factor. They experience only approximately 48,400 years. 48,400 years is still an enormous duration. It spans roughly the time from the late Pleistocene, when our ancestors were painting caves at Lascaux and hunting woolly mammoths across Ice Age Europe, to the present day. But it represents a reduction by more than half compared to the observer's time. Relativity is now doing serious work. The travelers are aging at less than half the rate of the civilization they left behind. When they arrive at the far edge of the galaxy, 111,000 years have passed in the rest of the universe. Civilizations have risen and collapsed many times over. But on the ship, only 48,000 years have elapsed. The travelers are, in a very real sense, time travelers. They have skipped forward through 63,000 years of external history by moving fast enough to make their own time flow more slowly. At 99% of light speed, the distortion becomes dramatic. The Lorentz factor jumps to approximately 7.09. The observer sees the ship cross the galaxy in approximately 101,000 years, essentially just a hair longer than the light travel time itself, since the ship moves at 99% of light speed. But the travelers experience only approximately 14,300 years. 14,300 years. That is roughly the time since the end of the last ice age, since humans first began experimenting with agriculture, since the earliest permanent settlements appeared in the Fertile Crescent. The entire arc of human civilization from the first villages to the modern world fits within 14,000 years. A crew that departed at 99% of light speed would experience a journey spanning the same duration as recorded human cultural development. Immense, but no longer incomprehensible. For the first time in our calculations, the experienced travel time falls within a range that human societies have actually existed, but we can push further still. 99.9% of light speed. The Lorentz factor soars to approximately 22.4. The observer sees the crossing take roughly 100,100 years, essentially indistinguishable from light travel time. But the travelers experience only approximately 4,500 years. 4,500 years. That is the span from the construction of the Great Pyramids at Giza to the present day. From the earliest Egyptian dynasties, through the rise of Greece and Rome, through the Middle Ages, the Renaissance, the Industrial Revolution, and the Space Age. The entirety of what we typically call recorded human history fits within this window. At 99.9% of light speed, a crew could theoretically cross the entire Milky Way galaxy, while experiencing less subjective time than has elapsed since the Bronze Age. The universe outside the ship would age by 100,000 years. Stars would be born and die. Civilizations that existed when the ship launched would be ancient history. Their ruins crumbled to dust. But inside the ship, the travelers would have aged by only 45 centuries. They would arrive at the far edge of the galaxy as temporal exiles, stranded 100,000 years in the future of a universe that barely remembers them. This is the power and the cruelty of relativistic time dilation. It compresses the traveler's experience while doing nothing to compress the external reality. The galaxy is still 100,000 light-years wide. The crossing still takes approximately 100,000 years from the perspective of anyone not on the ship. Relativity does not shrink the galaxy. It shrinks the traveler's experience of crossing it. The universe pays the full price in time. The travelers get a discount, but only on their own clocks. There is a hard mathematical flaw that no amount of velocity can break through. Even if you could travel at exactly the speed of light, which is physically impossible for any object with mass, the crossing would take 100,000 years from the external observer's perspective. Time dilation at light speed would theoretically reduce the traveler's experience time to zero, but this limit is asymptotic. You can approach it but never reach it. At 99.99% of light speed, the traveler would experience roughly 632 years. At 99.999%, roughly 200 years. The numbers keep shrinking but never reach zero, and the energy costs of each additional decimal place of velocity escalate catastrophically, which brings us to the brutal reality of what these speeds actually require in terms of energy. Accelerating a spacecraft to relativistic velocities is not merely an engineering challenge. It is a confrontation with the most fundamental constraints of physics. The kinetic energy of a moving object increases with velocity, but at relativistic speeds, that increase becomes savage. At low velocities, doubling the speed quadruples the energy. At relativistic velocities, the energy climbs toward infinity as the speed approaches light. Consider a spacecraft with a modest mass of 1,000 tons, roughly the weight of a large naval destroyer. To accelerate this craft to 10% of light speed requires approximately 4.5 times 10 to the 26th joules of energy. That is roughly the total energy output of the Sun over an entire day. To accelerate the same spacecraft to 90% of light speed requires approximately 1.3 times 10 to the 28th joules. That is roughly the Sun's total energy output over 300 days, nearly an entire year of solar output for a single spacecraft. At 99% of light speed, the energy requirement climbs to approximately 6.1 times 10 to the 28th joules. This exceeds the total annual energy output of the Sun. To push one object weighing roughly what the International Space Station weighs to 99% of light speed, you would need to capture and convert more energy than the Sun produces in an entire year. Every photon, every particle of solar wind, every erg of fusion energy from that 4.6 billion-year-old nuclear furnace, all of it, and more, directed into accelerating a single ship. And that calculation only covers acceleration. The spacecraft also needs to decelerate at the destination unless you plan to streak past the far edge of the galaxy at 99% of light speed without stopping. Deceleration requires the same energy investment as acceleration. The total energy budget doubles. 2 years of solar output for a round trip of acceleration and deceleration for a single ship. The fuel problem compounds the energy problem mercilessly. Any conventional rocket must carry its fuel with it, and the fuel itself has mass that must also be accelerated. This creates a vicious exponential relationship where the fuel needed to accelerate the payload, quickly dominates the entire mass budget. For a chemically fueled rocket, reaching even 1% of light speed would require a fuel-to-payload ratio so extreme that the rocket would need to be larger than a planet. For nuclear propulsion, the ratios improve but remain staggering. Even antimatter propulsion, the theoretical ceiling of fuel efficiency we explored earlier, would require thousands of tons of antimatter to accelerate a modest payload to 99% of light speed. As we established, global production amounts to approximately 10 nanograms per year, making the required quantities utterly unattainable at any foreseeable production rate. The perfect fuel remains effectively non-existent at the scales relativistic travel would consume. These energy requirements are not engineering problems waiting for clever solutions. They are expressions of fundamental physics. The relativistic mass-energy relationship discovered by Einstein dictates that as an object approaches the speed of light, the energy required to accelerate it further approaches infinity. No propulsion system, no matter how advanced, can circumvent this relationship. It is woven into the structure of space-time itself. There is a practical complication that every calculation so far has quietly ignored. We have been assuming that the spacecraft simply starts at its cruising velocity and maintains it across the entire 100,000 light-year distance. In reality, no spacecraft begins its journey already moving at 99% of light speed. It must accelerate from rest, gradually building velocity over an extended period. And unless the goal is simply to streak past the far edge of the galaxy without stopping, the ship must also decelerate at the destination, shedding all that hard-won velocity to arrive at a manageable speed. Both phases take time, and during both phases, the ship is moving slower than its maximum cruise speed, which adds to the total journey duration. The rate of acceleration matters enormously for the crew. Human bodies can tolerate sustained acceleration of approximately 1 g, equivalent to the gravitational pull at Earth's surface, indefinitely without adverse health effects. This is the most commonly discussed acceleration profile for crewed interstellar missions. At a constant 1 gig acceleration, a spacecraft reaches remarkable velocities, surprisingly quickly by human standards. After 1 year of continuous 1 g thrust, a ship reaches approximately 77% of light speed. After 2 years, it exceeds 97% of light speed. The math here incorporates relativistic effects. Since Newtonian calculations break down at these velocities, relativistic acceleration under constant proper thrust follows a hyperbolic trajectory through space-time rather than a simple linear velocity increase. To reach 99% of light speed at 1 g acceleration requires approximately 3 years and 2 months of ship time. That sounds remarkably short compared to the crossing times we have been discussing. But remember that during this acceleration phase, the spacecraft is not yet at cruise speed. it covers less distance per unit time than it will at full velocity. The distance consumed during acceleration to 99% of light speed at 1g amounts to roughly 2.5 light-years. The same distance is consumed during deceleration at the destination. Together, approximately 5 light-years of the crossing are spent in acceleration and deceleration phases. Against a 100,000 light-year crossing, this is negligible, less than 1/100th of 1% of the total distance. But the situation changes dramatically at lower accelerations. If the spacecraft can only sustain 1/10 of a g, perhaps due to engine limitations or structural constraints, reaching 99% of light speed takes roughly 32 years of ship time. The distance consumed during acceleration stretches to roughly 25 light-years, and deceleration adds another 25. Still small against the galactic diameter, but the time spent not at cruise speed now represents decades of additional journey duration. More critically, acceleration phases consume enormous quantities of fuel or energy. Every propulsion system that uses onboard fuel faces the brutal reality that fuel expended during acceleration reduces the fuel available for the cruise phase and deceleration. For antimatter or fusion drives, the fuel mass required for acceleration, cruise, and deceleration must all be carried from the start, and the rocket equation ensures that each phase's fuel requirement compounds exponentially. A spacecraft designed to accelerate to 99% of light speed, cruise for 100,000 light-years, and then decelerate to rest at the destination requires more than twice the fuel of a spacecraft that merely reaches cruise speed. Because deceleration demands an entirely separate fuel budget, roughly equal to the acceleration budget. This is why some theoretical mission designs propose one-way flyby missions with no deceleration, sacrificing the ability to stop at the destination in exchange for dramatically reduced fuel requirements. A civilization that merely wants to observe the far edge of the galaxy as it screams past at 99% of light speed could cut its energy budget roughly in half. But any mission that intends to arrive, to explore, to settle, must pay the full energy price twice. Once to speed up, once to slow down. The galaxy charges admission in both directions, but energy is not the only adversary a relativistic spacecraft faces. The interstellar medium, the thin gas and dust that fills the space between stars, transforms from a minor nuisance into a lethal hazard at relativistic velocities. The average density of the interstellar medium in our region of the galaxy is roughly 1 hydrogen atom per cubic centimetre. At rest, this is an almost perfect vacuum, far emptier than anything achievable in terrestrial laboratories. But at relativistic speeds, these sparse atoms become deadly projectiles. The kinetic energy of a particle is determined by its relative velocity. A hydrogen atom striking a spacecraft at 99% of light speed carries kinetic energy equivalent to roughly 600 million electron volts. That is not just fast. That is the energy regime of a high-energy particle accelerator. Each hydrogen atom becomes a cosmic ray, slamming into the hull with enough energy to damage molecular bonds, degrade materials, and generate cascades of secondary radiation inside the ship. At 90% of light speed, a spacecraft with a cross-sectional area of 100 square meters would sweep up approximately 30 trillion hydrogen atoms per second, each one carrying hundreds of millions of electron volts of kinetic energy. The cumulative radiation dose would be catastrophic for both biological passengers and electronic systems. Shielding against this bombardment requires mass, which requires more energy to accelerate, which deepens the fuel problem even further. Dust grains present an even more immediate threat. A typical interstellar dust grain has a mass of roughly 10 to the negative 12 grams, 1 trillionth of a gram. At 99% of light speed, this microscopic particle carries kinetic energy equivalent to roughly the detonation of several kilograms of TNT. A grain of dust becomes a bomb, and the interstellar medium contains roughly 1 dust grain per 100,000 cubic meters. At relativistic velocities, a spacecraft would encounter hundreds of these micro-impacts per second, each one delivering explosive force to the hull. Over a journey of thousands or tens of thousands of experienced years, the cumulative damage would be devastating without shielding technology far beyond anything currently conceivable. Some proposals suggest generating powerful magnetic fields ahead of the spacecraft to deflect charged particles, creating a kind of electromagnetic bow shock that sweeps the interstellar medium aside before it reaches the hull. This concept works in principle for charged hydrogen atoms, but fails for neutral particles and dust grains. Other proposals envision physical shielding layers that ablate over time, sacrificing material to absorb impacts. But any shielding adds mass, and mass is the mortal enemy of relativistic propulsion. The engineering challenges cascade in every direction, each solution generating new problems that demand their own solutions. Let us now stand back and confront the central insight that emerges from this entire analysis. Even at 99.9% of light speed, the most extreme velocity we can meaningfully calculate, the traveller still experiences approximately 4,500 years of subjective journey time. That is not a quick trip. That is the entire span of recorded human civilization experienced inside a metal container, hurtling through interstellar space at nearly the maximum speed the universe permits. The energy required to achieve this velocity exceeds the annual output of the Sun. The radiation hazard from the interstellar medium would destroy any known material or biological system. And the external universe ages by 100,000 years while the travellers experience their 45 centuries. Light speed is often presented in popular culture as the ultimate solution to cosmic distances. If only we could travel at the speed of light, the galaxy would be accessible. This is wrong. Light speed is not a solution. It is barely a compromise. Even photons, travelling at the absolute maximum velocity physics permits, require 100,000 years to cross the galaxy. Relativity offers the traveller a subjective discount on that time, and the discount grows more generous as you approach light speed more closely. But it never reaches zero. And the costs of claiming each additional percentage point of discount in energy, in shielding, in engineering complexity escalate exponentially toward infinity. The galaxy is 100,000 light-years wide, and no amount of velocity can change that fundamental fact. What relativity changes is the experience of the crossing, not the crossing itself. The universe still ages, the stars still turn, the civilizations you left behind still crumble and are replaced. You simply arrive having aged less than everyone else, a stranger in a future that has no memory of your departure. There is one more critical complication we have ignored throughout every calculation so far. Every number we have computed assumes the galaxy is a static target, a fixed 100,000 light-year disk hanging motionless in space, waiting patiently for your spacecraft to traverse it. The Milky Way is not static, it is not motionless, it is not waiting. Our galaxy is a living, rotating, dynamically evolving structure where stars move independently. The disk spins at hundreds of kilometers per second, and the destination you are aiming for is not where it will be when you arrive. The galaxy is a moving target, and that changes every calculation we have made in ways that are profoundly unsettling. The crossing just got harder, much harder. Every calculation we have made so far contains a hidden assumption so fundamental that you probably did not even notice it. We treated the Milky Way as a frozen object, a static disk of stars hanging motionless in space like a photograph pinned to a wall. We measured the distance, picked a speed, divided one by the other, and called the result a travel time. The math was clean, the logic was straightforward, and the assumption underneath all of it was completely wrong. The Milky Way is not frozen, it is not static, it is not hanging motionless anywhere. Our galaxy is spinning. It has been spinning for over 13 billion years. Every star in it, including our Sun, is hurtling along its own orbital path around the galactic center at speeds that would obliterate any earthly frame of reference. And this rotation does not pause politely while a spacecraft tries to cross from one edge to the other. The galaxy keeps moving during the journey. Your destination keeps moving during the journey. The The place you aimed for when you launched is not where it will be when you arrive. The Milky Way is a moving target, and that changes everything. Before we examine how galactic rotation reshapes the crossing problem, consider for a moment what the galaxy would actually look like from inside a spacecraft moving at relativistic velocities. The visual experience of near light-speed travel is nothing like what science fiction typically portrays. There are no graceful star streaks sliding past the windows, no gentle blur of passing light. The reality, confirmed by the equations of special relativity, is far stranger and far more alienating. At velocities approaching the speed of light, a phenomenon called relativistic aberration compresses the apparent positions of stars toward the direction of travel. Stars that would normally be visible off to the sides or even slightly behind the spacecraft appear to crowd forward, concentrating into a shrinking disk of light directly ahead. At 90% of light speed, stars that are actually positioned 90 degrees to the side of the ship, directly abeam, appear to be only about 26 degrees ahead of the forward direction. The entire visible sky collapses toward the front of the vessel. Behind the ship, the sky grows increasingly dark and empty as stars that should be visible in the rear hemisphere are aberrated forward. Simultaneously, the Doppler effect transforms the color of every star depending on its apparent direction. Stars ahead of the spacecraft have their light compressed to shorter wavelengths. Visible starlight shifts into the ultraviolet and then into X-ray frequencies, becoming invisible to the naked eye, but increasingly dangerous as high-energy radiation. Stars to the sides shift blue. Stars behind, the few whose light still reaches the rear-facing windows, shift dramatically toward the red and infrared, fading from visibility into wavelengths human eyes cannot detect. The net effect is haunting. The forward sky becomes a blazing, concentrated disk of blue-white brilliance surrounded by a growing ring of darkness. The rearward sky becomes a black void. The familiar constellations vanish completely, replaced by an alien light show that bears no resemblance to any sky visible from Earth. At 99% of light speed, the forward compression becomes extreme. Nearly the entire observable sky is squeezed into a small, brilliant cone ahead, while the rest of the celestial sphere appears completely black. The cosmic microwave background radiation, normally invisible microwave frequency photons left over from the Big Bang, gets Doppler shifted into visible wavelengths directly ahead, adding an eerie glow to the forward disk. The travelers would see the echo of the universe's birth shining ahead of them as visible light, blue shifted from its normal microwave frequencies by their enormous velocity. This visual transformation is not merely a curiosity, it has practical implications for navigation. Familiar stellar reference points used for course correction become unrecognizable at relativistic speeds. The entire framework of positional astronomy, constellations, reference stars, angular measurements must be recalculated for the aberrated, Doppler-shifted sky. Navigation at relativistic velocities requires instruments and techniques completely unlike those used in conventional spaceflight, adding yet another layer of complexity to an already staggering challenge. Our Sun orbits the center of the Milky Way at approximately 220 kilometers per second. That is roughly 792,000 kilometers per hour, or about 492,000 miles per hour. At this velocity, the Sun and its entire retinue of planets, moons, asteroids, and comets complete one full orbit around the galactic center, approximately every 220 to 230 million years. Astronomers call this period a galactic year. Since the Sun formed roughly 4.6 billion years ago, it has completed only about 20 full orbits. The solar system has circled the galaxy fewer times than you have fingers. Each galactic year, the Sun travels a path roughly 140,000 light-years long, threading through spiral arms, crossing interarm gaps, drifting slightly above and below the galactic midplane, in a gentle oscillation that takes tens of millions of years per cycle. But here is the critical detail that transforms our crossing problem from difficult to genuinely bewildering. The galaxy does not rotate like a solid wheel. If it did, Stars at all distances from the center would complete their orbits in the same amount of time, with outer stars simply moving faster to cover their larger orbital circumferences. This is not what happens. The Milky Way exhibits differential rotation. Stars closer to the galactic center orbit faster in angular terms, completing their circuits in less time than stars farther out. Stars in the inner galaxy at roughly 10,000 light-years from the center might orbit in as little as 100 million years. Stars in the outer disk at 60,000 or 70,000 light-years out might take 300 million years or more. Our Sun, at 26,000 light-years from center, splits the difference at approximately 225 million years. This differential rotation means that the galaxy is constantly shearing. Inner regions slide ahead of outer regions. Stars that were once aligned radially, forming a straight line from center to edge, gradually smear out into curves as inner stars pull ahead. The spiral arms themselves are manifestations of this differential rotation, interacting with density wave patterns that propagate through the disk. The galaxy is a fluid, dynamic structure in constant rotational motion, with every annular ring of stars moving at its own angular velocity. Now consider what this means for a spacecraft attempting to cross 100,000 light-years of galactic diameter. Suppose you identify a target star on the far edge of the galaxy, directly opposite your starting position. You calculate the distance at 100,000 light-years, select your speed, and launch. But the moment you depart, that target star begins sliding sideways along its own orbital path. If you are traveling at 10% of light speed, the crossing takes 1 million years. During that 1 million years, your target star, orbiting at its own velocity of perhaps 150 to 200 kilometers per second, covers an enormous arc of its galactic orbit. Let us calculate the drift. A star orbiting at 200 kilometers per second covers approximately 6.3 trillion kilometers per year. Over 1 million years, that accumulates to roughly 6.3 quintillion kilometers, which converts to approximately 667 light-years of lateral displacement. That might sound manageable against a 100,000 light-year crossing, but this calculation only accounts for the target star's motion. Your origin point is also moving. The Sun is orbiting at 220 kilometers per second in its own direction. The angular difference between your orbital path and the target star's orbital path depends on galactic geometry, and because of differential rotation, the two stars are not moving in parallel. They are moving at different angular velocities depending on their respective distances from the galactic center. Over a million-year journey, the cumulative angular displacement between your departure point and your arrival target could amount to several degrees of galactic longitude. In a galaxy 100,000 light-years across, even a single degree of angular error translates to roughly 1,700 light-years of lateral miss-distance at the far edge. A few degrees of error puts you thousands of light-years from where you intended to be. You would arrive at empty interstellar space, your target star long gone from the position it occupied when you launched, orbiting serenely thousands of light-years away from your arrival point. At slower speeds, the problem becomes catastrophic. Consider Voyager 1's crossing time of 1,760,000,000 years. During that span, the Sun itself would complete roughly 8 full orbits of the galactic center. The target star would complete a different number of orbits depending on its own orbital radius. The angular positions of departure and destination would have no meaningful relationship to their positions at launch. You would not just miss the target. The entire geometric concept of aiming at a fixed destination becomes meaningless. Over billions of years, stars redistribute themselves around the galactic disk in ways that bear no resemblance to their starting configuration. Targeting a specific star for a billion-year journey is like throwing a dart at a carousel and expecting to hit a specific horse after the carousel has completed hundreds of revolutions. But differential galactic rotation is only the most obvious source of navigational chaos. Individual stars also possess their own peculiar velocities, random motions superimposed on top of their regular galactic orbits. These peculiar velocities arise from gravitational interactions with neighboring stars, encounters with molecular clouds, and the residual momentum from the star's original formation environments. Typical peculiar velocities for stars in the solar neighborhood range from approximately 10 to 50 kilometers per second relative to the local standard of rest. Some stars have significantly higher peculiar velocities, exceeding 100 kilometers per second, often as a result of close gravitational encounters or ejection from binary systems. Over short timescales, these random motions are small compared to galactic distances. A star moving at 30 kilometers per second covers roughly 1 light-year every 10,000 years. Inconsequential for everyday astronomy. But over the million-year and billion-year timescales relevant to galactic crossing, peculiar velocities accumulate enormously. Over 1 million years, a star with a peculiar velocity of 30 kilometers per second drifts approximately 100 light-years from its predicted position based on galactic rotation alone. Over 10 million years, the drift reaches 1,000 light-years. Over 100 million years, 10,000 light-years. These offsets compound the navigation problem created by differential rotation. Even if you could perfectly predict a target star's orbital motion around the galactic center, its random peculiar velocity would introduce positioning errors of thousands of light-years over crossing relevant timescales. Predicting where a specific star will be millions of years from now requires knowing its current position, its current velocity in 3 dimensions, and every gravitational perturbation it will experience along the way with extraordinary precision. This is functionally impossible. Gravitational interactions with passing stars are chaotic, meaning tiny uncertainties in current conditions amplify exponentially into massive uncertainties over long timescales. The trajectory of a star 1 million years into the future is fundamentally unpredictable beyond a certain precision threshold, just as weather on Earth becomes unpredictable beyond roughly 2 weeks. Stellar orbit prediction hits its chaos limit at timescales far shorter than the journey times we are discussing. This means any civilization attempting a galactic crossing cannot simply aim and fire. They must navigate continuously. Course corrections spanning the entire journey, recalculating the target's position in real time, adjusting trajectory to compensate for both the target's motion and the spacecraft's own interaction with the galactic gravitational field. The spacecraft must carry not just a propulsion system, but an ongoing astronomical observation and navigation capability sustained over millions of years. The galaxy's own motion through intergalactic space adds yet another layer of complexity, though this one primarily affects external perspective rather than internal navigation. The Milky Way moves at approximately 600 kilometers per second relative to the cosmic microwave background, the residual radiation from the Big Bang that serves as the closest thing the universe has to a universal rest frame. This motion carries the entire galaxy, every star within it, every spacecraft crossing it, through intergalactic space at breathtaking velocity. During a billion-year crossing at Voyager speeds, the galaxy itself travels approximately 190 million light-years through intergalactic space. The spacecraft is crossing the galaxy while the galaxy is racing through the cosmos. From an external perspective, the trajectory is not a straight line across a disk, but a long helical path spiraling through expanding space-time. This extragalactic motion does not directly affect the internal crossing calculation, because the spacecraft shares the galaxy's bulk motion. Everything inside the galaxy, ship and destination alike, moves together through intergalactic space, but it serves as a humbling reminder that the galaxy itself is not a fixed stage. It is a moving vehicle, and any crossing attempt occurs aboard that vehicle as it hurtles through a much larger cosmic arena. Now we must confront the deepest implication of everything we have discussed. Every propulsion challenge, every relativistic calculation, every navigational complication ultimately reduces to a single variable: time. And time is not a technological problem, it is a civilizational problem. Suppose humanity solves propulsion. Suppose we build engines capable of accelerating spacecraft to 10% of light speed, fast enough to cross the galaxy in 1 million years. The engineering is complete. The physics is satisfied. The ship is built and launched. What happens next? 1 million years of continuous operation. 1 million years during which the spacecraft must maintain structural integrity against micrometeorite impacts, cosmic radiation damage, material fatigue, and the slow degradation of every engineered system ever built. No human technology has survived even 10,000 years intact. The oldest functioning artifacts of our civilization are simple stone structures. Metals corrode, electronics fail, seals degrade. Lubricants evaporate. Radiation slowly scrambles the crystal structure of semiconductors. 1 million years of continuous operation in the harsh environment of interstellar space is not an engineering challenge in the conventional sense. It is a challenge that exceeds the demonstrated durability of every material, every system, and every design philosophy in human technological history by factors of hundreds. The ship must carry a living population. No single human lifespan covers more than a tiny fraction of even the most optimistic crossing times. A journey of 1 million years at 10% of light speed spans roughly 33,000 human generations, assuming an average generation time of 30 years. 33,000 generations of humans would live, reproduce, raise children, grow old, and die aboard this vessel. Each generation inheriting the mission from the previous one. Each generation trusting that the mission matters, that the destination exists, that arrival is worth the sacrifice of living and dying inside a metal container crossing the void between stars. The biological implications alone are staggering. Population genetics dictates that any closed population, no matter its starting size, will experience genetic drift over generations. Random fluctuations in gene frequency accumulate over time, gradually changing the genetic composition of the population in unpredictable ways. Over 33,000 generations, the magnitude of genetic drift would be enormous. If the founding population is small, genetic diversity would erode rapidly through inbreeding, leading to reduced fitness and potential population collapse. If the founding population is large enough to maintain genetic health, the resource demands of the ship increase proportionally. Natural selection would also operate on the ship's population, but under environmental conditions radically different from those under which humans evolved. The selective pressures aboard a generation ship, confined spaces, artificial gravity or microgravity, recycled atmosphere, limited diet, social stress from permanent close-quarter habitation, would favour traits very different from those selected for on the open African savanna. Over tens of thousands of generations, the ship's population would adapt to their artificial environment. They would become biologically specialised for life aboard a spacecraft. The beings who arrive at the destination after a million-year journey would not be Homo sapiens. They would be a new species, shaped by 1 million years of evolution in an environment that no human alive today would recognise as home. Culture would undergo equally radical transformation. No human culture has survived intact for more than a few thousand years. Languages drift into mutual unintelligibility within centuries. Religions, political systems, social structures, artistic traditions, scientific paradigms, all of these change continuously and often dramatically across generational timescales. Over 33,000 generations, the culture aboard the ship would reinvent itself thousands of times over. The mission itself, the reason for the journey, would need to survive these cultural upheavals. A civilization that launched the ship with a specific purpose, perhaps exploration, colonization, or scientific discovery, would need to transmit that purpose faithfully across more cultural generations than have occurred in all of human history combined. History offers no precedent for institutional continuity on this scale. The Catholic Church, one of the oldest continuously operating institutions on Earth, is roughly 2,000 years old, spanning perhaps 67 generations. The galactic crossing at 10% of light speed requires institutional continuity roughly 500 times longer. No organizational structure, no governance model, no cultural tradition in human experience has demonstrated anything approaching this kind of persistence. The challenge is not building a ship that can cross the galaxy. The challenge is building a civilization that can survive the crossing. This is where the Kardashev scale becomes relevant, not as speculative science fiction, but as a serious framework for understanding what galactic scale travel demands. In 1964, Soviet astronomer Nikolai Kardashev proposed classifying civilizations by their total energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the 16th watts. A Type 2 civilization captures the entire energy output of its host star, roughly 4 times 10 to the 26th watts. A Type 3 civilization commands the energy resources of an entire galaxy, roughly 4 times 10 to the 37th watts. Humanity currently rates approximately 0.73 on the Kardashev scale. We harness a fraction of Earth's available energy and a negligible fraction of the Sun's output. The energy requirements for relativistic galactic travel, as we calculated earlier, demand stellar-scale energy budgets. Accelerating even a modest spacecraft to 99% of light speed requires more energy than the Sun produces in a year. Doing this routinely, for fleets of ships sustaining a galactic crossing program, requires the energy infrastructure of at least a Type 2 civilization. But energy is only one axis of the challenge. The civilizational endurance required, millions of years of continuous technological and social coherence, arguably demands Type 2 or Type 3 organizational capacity as well. A civilization that can sustain a galactic crossing must have solved not just energy production but also governance across deep time, biological maintenance across evolutionary timescales, and cultural transmission across tens of thousands of generations. These are challenges that no human society has ever faced, let alone solved. Some theorists propose that truly advanced civilizations might sidestep the generation ship problem through suspended animation technologies, placing travelers in biological stasis for the duration of the journey and reviving them at the destination. This eliminates the generation ship challenges of cultural drift, genetic evolution, and institutional continuity. But it introduces its own problems. Maintaining biological stasis for millions of years requires technology so far beyond current capability that it borders on magic. Cryopreservation, the most commonly discussed approach, causes ice crystal formation that damages cellular structures. Even if perfected, maintaining cryogenic temperatures for millions of years inside a spacecraft, subject to cosmic radiation and system degradation, is a preservation challenge with no precedent in engineering history. Others propose digital consciousness transfer, uploading minds into computer systems that could be maintained more easily than biological bodies. A digital crew would not age, would not reproduce, would not evolve biologically, and could potentially be stored in compact, durable formats. But this approach assumes that consciousness can be meaningfully captured in digital form, a philosophical and neuroscientific question that remains entirely unresolved. It also requires computational hardware that functions without failure or degradation for millions of years, a challenge that mirrors the material durability problem in a different domain. The navigation problem we discussed earlier compounds the civilizational challenge. Continuous course correction over a million-year journey requires ongoing astronomical observation, trajectory computation, and propulsion adjustment. The spacecraft must carry not just a population or a stored consciousness, but an active, functioning, scientific and engineering capability that operates without interruption across the entire crossing. Any gap in capability, any period where the navigation system fails or the propulsion system degrades without repair, could result in the spacecraft drifting thousands of light years off course with no way to correct. Let us bring all of these threads together into a single, coherent picture of what crossing the Milky Way actually demands. The distance is 100,000 light-years. At any speed humanity currently possesses, the crossing takes billions of years. Even with the most advanced propulsion concepts ever seriously studied, the crossing takes millions of years. Even at 99% of light speed, the external universe ages by 100,000 years, and the traveller experiences 14,000 years. Even at 99.9% of light speed, the traveller still endures 4,500 years of subjective time. The galaxy rotates during the crossing, displacing targets by thousands of light years. Individual stars drift unpredictably due to peculiar velocities and chaotic gravitational encounters. The interstellar medium bombards the spacecraft with lethal particle radiation at relativistic speeds. The energy required for relativistic travel exceeds the annual output of our Sun. The ship must survive material degradation over timescales that exceed the lifespan of every human artifact ever created. The population must maintain biological viability across tens of thousands of generations. The culture must transmit mission purpose across more generations than have elapsed in all of human history. The navigation must function continuously, correcting for a galaxy that refuses to hold still. None of these challenges are prohibited by physics. That is the remarkable and frustrating truth. There is no law of nature that says a civilization cannot cross the galaxy. The speed of light imposes a minimum crossing time of 100,000 years for external observers, and time dilation can compress the traveller's experience to a fraction of that. Relativistic propulsion is permitted by physics, even if the energy costs are astronomical. Continuous navigation across a rotating galaxy is possible in principle, even if it requires technological sophistication far beyond our current capacity. Sustaining a civilization across millions of years is not forbidden by any natural law, even if no species on Earth has ever demonstrated such longevity in a technological state. The galaxy is not a wall, it is a filter. It does not block travel. It filters for civilizations capable of enduring on timescales that dwarf everything in human experience. Any species that crosses the Milky Way must have solved problems that our civilization has not yet even properly formulated. They must command energy on stellar scales. They must build machines that last for geological ages. They must maintain coherent purpose across evolutionary timescales. They must navigate a dynamic, rotating, gravitationally complex environment with precision sustained over millions of years. This is what separates galactic travel from interplanetary travel. Getting to Mars requires better rockets. Getting to the nearest star requires fundamentally new propulsion. Getting across the galaxy requires a fundamentally new kind of civilization, one that thinks in millions of years the way we think in decades. One that builds for eternity the way we build for quarterly earnings. One that treats the deep future not as an abstraction but as an operational planning horizon. The galaxy is 100,000 light-years wide. Light itself, the fastest phenomenon in nature, needs 100 millennia to span it. Our fastest spacecraft would need nearly 2 billion years. Our most ambitious theoretical engines would need millions. Even at velocities that distort the fabric of space-time, the crossing demands thousands of years of experience time and 100,000 years of external time as an absolute minimum. And throughout every second of that journey, the galaxy keeps turning, stars keep drifting, the destination keeps moving, the cosmos keeps aging. The universe does not pause for travelers, no matter how fast they fly or how ambitious their mission. Crossing the Milky Way is not impossible. Physics permits it. But physics also prices it. The cost is not measured in dollars or kilograms of fuel. It is measured in time, in centuries and millennia, and millions of years of sustained civilizational effort. The galaxy is not a barrier made of distance, though the distance is staggering. It is not a barrier made of energy, though the energy demands are immense. The galaxy is a barrier made of time. And time is the one resource that no engine can generate, no technology can manufacture, and no civilization can escape. That is the true cost of crossing our galaxy, not the miles, not the fuel, the years. The incomprehensible, humbling, staggering weight of years required to traverse a structure so vast that it reduces every human achievement to a footnote in a story that has barely begun. We built Voyager. We split the atom. We walked on the moon. We photographed a black hole. And all of it, every triumph of our species, amounts to the first half step on a journey that would take 1,000,000 lifetimes to complete. The Milky Way is waiting. It has been waiting for 13 billion years. It can wait a while longer. The question is not whether the galaxy can be crossed. The question is whether any civilization will ever endure long enough to do it, and if one does, they will have earned something that no species in the history of our galaxy may have ever achieved. Not just a destination on the other side, but proof that intelligence, once kindled, can burn long enough to outlast the stars that gave it birth.